Hey students, in this video we're going to talk about integrating over non-rectangular regions. So for this video we're going to consider only integrating over regions that are contained between a series of functions. Um, Procedurally and analytically, this is not different from what we did in 13.1. We have to identify an outer set of limits and an inner set of limits. But since the function is not rectangular, one of our sets of limits is going to be a function, and the outer limits always have to be two numbers. Um, so for this first example, we have the region bounded by y equals x squared and y equals 2x. So just in the xy plane, you could draw how this region would look. Um, So y equals x squared. We know 0, 0 is on that graph. We know the point 1, 1 is on the graph, and we know 2, 4 is on the graph. So we get a region that looks like that. And then the line y equals 2x when x is 1, y is 2, and when x is 2, y is 4. So we get a region that looks something like that. So now imagine that we gave this function a height if we gave this region a height above the XY plane, whatever we would get bounded between that, that's our volume. So I made this thing in GeoGebra where we actually have this. So, all right, so when we look at the function, it's exactly what we just drew. It's the line is on top, the parabola is on the bottom, and this surface, h of x equals x squared plus y, is this whole, we'll say like this whole pink region that we have here. What we want is just the volume that is under that surface on this region. So it looks like this. Um, so to get that, so we can clearly see that our limits for integration are from 0 to 2, and so when we're doing our two integrals in one direction, we have two x's on top, and then here we have x squares on the bottom. But we're also going from left to right, and considering we start at 0 and we go to 2. So if you think about this being on a rectangular region, once we fix this to be a function, we're like omitting the parts that aren't like in this rectangle that we've outlined. By making this a function, we've just taken out all of this like yellow region here. We've just taken that integral that would have been, we'll say, from like 0 to 4 and from 0 to 2, we just taken that part out. So when we integrate this procedurally, like I said, it's not any different from what we already know how to do. It's actually setting up the region that is the work. So like say we didn't have graphing capabilities and we had to find our limits for integration. So we know that the inner function is going to have limits that are from x squared to 2x. But then our outer limits, you would have to set those bounding functions equal to each other to find the limits. So you would look for where 2x is equal to x squared, which is the same as 0 equals x times x minus 2. And so we would get x equals 0 and x equals 2 as our two limits for integration. So our outer integral is from 0 to 2, and we'll write this in a different color. We'll say our inner integral is from, what was it, x squared to 2x, and we're integrating over this, under this surface. So that is x squared plus y dy and dx. So for the inner integral, we're going to get, so y is the variable for integration. So we're going to get x squared y plus y squared over 2. And we want to evaluate that from x squared to 2x. So when we substitute in 2x, we're going to get x squared times 2x, which is going to give us 2x cubed. And then we're going to get 2x squared divided by 2. So 2x squared is 4x squared, and we divide that by 2. So we're going to get plus 2x squared. And then we subtract, when we substitute in x squared times x squared is going to give us x to the fourth. And then x squared divided by 2 is going to be x to the fourth divided by 2. So if we simplify this, we get, all right, so this is going to be 3 halves x to the fourth, and then we distribute our negative. So we get negative 3 halves x to the fourth, and then we just have plus 2x cubed plus 2x squared. Cool. And so let's change it up. Our outer integral is going to be from 0 to 2, and we're just integrating this function. So negative 3 halves x to the fourth plus 2x cubed plus 2x squared dx. And again, the integration should be relatively easy. We should get negative 3x to the fifth divided by, let's see, 5 times 2 is 10. Then we're going to get plus 2x to the fourth divided by 4, so that's 1/2. And then plus 2x cubed divided by 3, and we're evaluating from 0 to 2. So if we substitute in 2, we're going to get 2 to the fifth is 32, and times negative 3 is negative 96. So we get negative 96 divided by 10. 2 to the fourth is 16, times 2 is 32, divided by 4 is 8, and 2 cubed is 8, times 2 is 16, so plus 16 thirds. And let's see, 2 divides into that, so we get negative 48 over 5. And say we get a common denominator. You know what? We get a common denominator of 15. So this was negative 48 over 5. So that's the same as negative 144 divided by 15. That is 8 times 15 is 120. So plus 120 over 15 and multiply that by 5, we get 80. So 80 over 15. And what's that? 200 minus 144. So 56 over 15, which is like 3 point something. What's that? 3 and 11/15? Who knows? So let's throw. I already threw this into Desmos. Yes, 3.73 as a fraction. It's 56 over 15, which is exactly what we got. Cool. So now that we see what we're doing, like we don't have to like actually graph all of these. Analytically, we need to be able to find the intersection points so that we can find our limits for integration. So for the second example, we have the volume bounded by the region 5 minus y and x equals y minus 2. All right, so I graphed this one as well, just so we can see what's happening. Let's take a screenshot of this, and we'll. All right, so it's important here that you choose the correct variables for integration. We'll make this a little lighter. So what we're doing is we're integrating over this region. And again, there's some surface that is above that. This is on the XY plane, and there's some surface that is above this who has a volume over this region. Now, there are two ways to integrate this. One way we could go vertically where we could integrate, we'll make that actually thicker now. So one way we can integrate, we could go from top to bottom. But the problem is we have two different functions. The purple line is the line x equals y minus 2. And then, so that would be from like, what, -1 to 1.5. And then we'd also have to integrate again from 1.5 to 4, where we have this other function. Now, if we integrate from left to right, we eliminate having to have two separate integrals. Instead, if we integrate from left to right, one line is always behind the other line. So if we integrate from left to right, we would have the red graph. So this is our rightmost function, and this is our leftmost function. So we have the right minus left. And so then we can find our limits, our intersection point, which is, it seems like it's 3.5, but again, we can find that analytically. So that's what we're doing. We don't need that. So let's hop back over to our notes. So we said that this one was the function on the right. This is the function on the left. So we need to find our intersection value when 5 minus y equals y minus 2. That's the same as 7 equals 2y. So clearly 3.5 equals y, or 7 halves equals y. However you want to think about it. So, oh, and we're also bounded by the line y equals 1. So our limits for integration are y equals 1 and y equals 7 halves. So those are our outer limits. So we'll first write our outer limits from 1 to, we'll say 3.5. And then our inner limits are, so the left function was y minus 2. The right function was 5 minus y. And we're integrating the function x, y. And this time, x is the variable being integrated first. So when we integrate this, since x is the variable for integration, we're going to get x squared over 2 times y, and we're evaluating from y minus 2 to 5 minus y. So the first thing I would do is, since we only need to substitute in stuff for x, I would factor out this y over 2 for a moment. It makes some of our calculations easier. So we're going to have whatever we get, we'll just multiply by y over 2 at the end. And so internal to this, when we substitute in 5 minus y, we're going to get 5 minus y squared minus y minus 2 squared. And if we remember Pascal's triangle, this is going to be 25 minus 10y plus y squared. And then here we're going to get y squared minus 4y plus 4. But then we have to distribute a negative. So when we combine like terms, internal, we're going to have y over 2. So 25 minus 4 is going to be 21. Negative 10 plus 4 is going to be minus 6y. Man, the thing is too large. So we had 21 minus 6y. And then the positive y squared. So you know what? We'll just switch the signs. So that's negative, that's positive, and that's negative. So y squared minus y squared is 0. So we get 21 minus 6y. And now when we distribute the y over 2, we get 21y over 2 minus 3y squared. I kind of want to just keep the half out of that. Yeah, you know what? Let's keep the half out. It won't matter. So let's make this 1/2 times 21y minus 6y squared. Cool. So what we need to integrate is from 1 to 3.5. And we're integrating 1/2 times 21y. And again, the half can go in the front if we actually want. So minus 6y squared. That's going to equal 1/2 times the antiderivative of 21y, which is 21y squared over 2. And then minus 3y, minus 2y cubed, excuse me, minus 2y cubed, and evaluate it from 1 to 3.5. All right, kids, this is not an arithmetic video, so let's just throw this into not GeoGebra, Desmos, and see what we get as the answer. So our outer limits were, y minus 2, and the other limit was 5 minus y, and the outer limits were from 1 to 3.5. And we need this to be dx dy, which has a decimal, 32.0. Oh, it's not that function, it was xy. Yeah, so 17.1875. So this equals 17.1875. If we had a cleaner number than 3.5, we would do this by hand, but who has time to worry about decimals? All right, so one more example, and we'll call it quits. Let's do this one. So we have this function x equals y squared minus 3, and x equals 5 minus y squared. Again, we could graph this by hand, but let's throw this into Desmos as well. So we get x equals 3 minus y squared. Was it y squared minus 3? Or was y squared minus 3? So x equals y squared minus 3. And the other one was x equals 5 minus y squared. Cool. So again, we want there's some function above the xy plane, and we're integrating the volume over this region. So again, let's screenshot this and annotate on it. So again, we could, like, the order in which you choose your variables for double integration really determines how hard your integral will be. So if we consider going from left to right, that we would have the 5, this is 5 minus y squared, and here we have y squared minus 3. So if we're integrating over this region going from right to left, everything is always a difference of the two functions. We can always do y minus x. So again, think about taking this rectangular region. I drew a terrible rectangle, don't judge me. So think about taking that rectangular region. Actually, you want to say is from here to here. So, and you just want to take out like the part that's outside of the you want to take out the part that's the frame part of the rectangle. So we only want this internal part. So to do that, we'd have to take out the function part. And so that's going to be this y squared minus 3 and 5 minus y squared part. And so again, we can find our upper limits where they intersect by just setting the functions equal to each other. We can just do that here, actually. So now we'll do it in the notes. So what we want is y squared minus 3 equals 5 minus y squared. So 2y squared equals 8, and y squared equals 4. So y equals positive and negative 2. So those are going to be our y limits for integration. So our outer integral is from -2 to 2, and our inner function is the right function minus the left. So the right function was, the function that was on the left, was y squared minus 3. So y squared minus 3. And the right function was 5 minus y squared. And we're integrating over that function, under that function. So y, and then we're going to have dx dy. So this is actually pretty straightforward. So since y is a constant, what we're going to get first is just x times y evaluated from y squared minus 3 to 5 minus y squared. That's going to equal x times 5 minus y squared minus x times y squared minus 3. If you wanted to simplify, that would be 5x minus xy squared minus xy squared plus 3x. So we end up with 8x minus 2x y squared. And now we want to integrate, why did I substitute in x? Hold on a moment. Ms. Smart, I think you're going crazy. We want to substitute 5 minus y squared and for x. You know what? These should all be y's. I'm a crazy person. Insane mistake. Hold on a minute, kids. Let's start that over. So when we substitute in 5 minus y squared for x, the right way, so we have 5 minus y squared times y minus y squared minus 3 times y. That's going to give us 5y minus y cubed minus y cubed plus 3y. Why did pen stop writing? So plus 3y. So that is 8y minus 2y cubed. Whew, crazy. And so now we want to integrate from -2 to +2 of 8y minus 2y cubed dy, and that's going to be 4y squared minus y to the 4th over 4, evaluated from -2 to 2. And yeah, I guess we can do this one algebraically. So we'd have 2 squared is 4, 4 times 4 is 16. 2 to the 4th is 16 divided by 4 is 4. So 16 minus 4 minus, honestly, the same thing. So when we substitute in -2, is it actually 0? Huh. That's interesting. We'll graph this one in class. So -2 squared is 4. 4 times 4 is 16. And then -2 to the 4th is 16 divided by 4 is 4. So 16 minus 4. And that's going to give us 12 minus 12, which is 0. All right. So that means that we have a net volume of 0 on that region. That would mean that we would have to have, like, say from -2 to 0, there's a portion below the xy plane. And then from 0 to 2, there's a portion above the xy plane. And so they would cancel each other out. We'll grab this one in class, though. Interesting one. And you know what? We'll grab this in class, and you'll learn how to make that thing I made in GeoGebra. All right. So that's our video on double integrals over non-rectangular regions. Same as 13.1, except it's not rectangular. All right. See you in class.